Imagine the long-standing mystery at the crossroads of gravity and quantum mechanics finally inching closer to resolution. Sounds revolutionary, right? But here's where it gets controversial. New insights suggest that we might not need revolutionary new tech to probe this connection after all. Instead, existing matter-wave interferometers, devices designed to measure the delicate quantum phases of particles, could hold the key to demonstrating that gravity indeed fosters quantum entanglement between systems. And this is the part most people miss. By confirming the Schrödinger equation's validity for a single delocalized quantum system interacting with a mass, scientists can indirectly verify that a pair of such systems will inevitably become entangled through gravitational interactions. This breakthrough dramatically narrows the gap between theory and achievable experiment, hinting that verifying quantum gravity may be closer than previously believed, perhaps even within our current technological reach. Quantum physics has achieved remarkable success in explaining the microscopic world, yet binding it to the fabric of gravity has remained an elusive goal. The challenge lies in the fact that experiments directly measuring gravitationally induced entanglement between large objects are often considered far beyond our current capabilities. Until now, recent proposals suggest that our existing sophisticated matter-wave interferometers are sensitive enough to detect the subtle fingerprints of gravity doing what we thought was purely classical, generating entanglement between quantum entities. The crux of the new approach is that verifying the Schrödinger equation for a single quantum system, specifically one that is deliberately placed into a superposition of positions, can imply that another similar system will become entangled with it via gravity. This link between simple quantum tests and complex gravitational effects opens a promising pathway toward understanding the quantum essence of gravity. The researchers outline a meticulous experimental design involving mesoscopic masses, objects small enough that quantum effects are observable, but large enough that gravity's influence is measurable. By putting these masses into superpositions of different spatial states and then bringing another mass into a similar quantum state nearby, the gravitational interaction should induce entanglement detectable via phase shifts in an interferometer. Their detailed theoretical models and numerical simulations demonstrate that even electromagnetic forces like the Casimir-Polder interaction can be controlled or minimized, allowing the gravitational effect to stand out. Interestingly, the team shows that even a weaker criterion, known as a positive map condition, suffices to confirm entanglement, broadening the experimental conditions under which these effects can be detected. To optimize the conditions and interpret results, the researchers employ advanced techniques like semi-definite programming, ensuring the setup maximizes the likelihood of observing gravitational entanglement. The entire process is supported by comprehensive simulations and theoretical calculations, which give a solid foundation for the experimental approach and help differentiate between classical and quantum effects induced by gravity. The work also pays careful attention to ruling out non-quantum classical influences, reinforcing that observed entanglement would be a true signature of gravity's quantum nature. Why does all this matter? Because it suggests that we can test one of the deepest questions in fundamental physics, whether gravity is inherently quantum, without waiting for pie-in-the-sky technology. Instead, our existing tools might suffice to capture the subtle dance of quantum states influenced by gravity. If validated, this approach could not only bridge the conceptual divide between quantum mechanics and Einstein's theory of general relativity, but might also unlock new understanding of the universe's origins and structure. And now, throw in this provocative thought. Could it be that gravity, long viewed as a classical force, is actually a consequence of deep-rooted quantum entanglement? If so, how might our universe's fabric fundamentally change our understanding of reality? These are the questions igniting curiosity and debate among physicists. Do you agree that these experimental advances could be a game changer? Or do you see limitations that might keep us from truly unraveling gravity's quantum thread? Share your thoughts, and let's stir the conversation about the true nature of the universe.